Okay, so this is homework 5, problem 1. And so, as an example, let's say we have a random variable z. And that random variable z is a summation of the random variables x and y. And so, we know that the probability mass function of z is simply just equal to the probability of where the random variable z is less than z. And so we can just substitute in x plus y for z here, and then we get the probability for where the random variables x and y are less than z. Now this is also equal to simply just the probability mass function of the random variables x plus y. And that is also equal to just the double integrals over the area under the line of where x plus y is less than or equal to z of the function of x and y of x and y dx dy. And so this could be written in two ways. Either you can solve for x, in which case x would be less than z minus y, and so x less than z minus y would look like this negative slope here of y up by a function up by z, and then x would be everything less than this line here. Similarly, if you wanted to solve for y would be then moving the x over to the other side. Y would just be less than z minus x. And so it would be like a similar graph, except you would just change the axes instead of going from y horizontally and x vertically. You have x horizontally and y vertically. So this is the axis we are probably more familiar with. So this graph will look like this. And so if you want to calculate big F of z, it's simply just like as we have up here, the double integral of the function f of xy dx dy over the bounds of where x and y exist. So if you're solving for where x is less than z minus y, then the bounds of x are from negative infinity to this function here of z minus y. And so your integral with respect to x will simply just go from negative infinity to z minus y, and then your bounds for y will simply just go negative infinity to infinity. And so afterwards, we say that the probability density function is equal to just the derivative of the probability mass function. So that we know is true. So then we know that the probability density function is just simply equal to the partial derivative with respect to z times the double integral that we had before. And so we can evaluate this double integral here simply to be, so for d, if we're doing with respect to x, so then for all x we just substitute in z minus y, and so we just get f of xy of z minus y comma y, and then we still have, so we did the inside integral that is simply just equal to this. And therefore, the outside integral is just simply negative infinity to infinity. We did x, so it's just dy that's left. So it's negative infinity to infinity of small xy of z minus y z dz. Similarly, we can also use a different method by just saying let's say we solve for y, and so the bounds instead of doing dx dy we do dy dx, and so the bounds of y are simply just going to be from negative infinity to the line of where it's z minus x. So that's the bounds of y, and then the bounds of x would simply just go from negative infinity to infinity. And so similarly like we did in the second step in the previous part here is the same, and the only thing different is that instead of going dx dy we just solve dy dx. So the bounds are from negative infinity to minus x instead of negative infinity to z minus x instead of negative infinity to z minus y. And so just like how we substitute in for z minus y for every x, we substitute in z minus x for every y, and this will be the evaluation for y. So essentially what we're doing is that if we're integrating with respect to y, we're eliminating the y component of the y component from the function, and then it'll be just in respect to x. So we substitute in this in for y, and we get negative infinity to infinity of the probability density function of xy of x comma z minus y dx. And so an interesting thing happens when the function is independent. If the two random variables, let's say up here x and y, are independent, then we can simply just take the density function is simply the density function of xy is simply just the density function of x, density function of x times the density function of y. So we can split up small f of xy into small f of x and then small f of y. Because the components are independent, we can multiply those two together. So the first component, small f of x, will be small f of x of z minus y, and the second component, f of y, would simply just be f of y dy. So this whole thing is dy over negative infinity to infinity. Similarly, for solving with regards to x, we can split this function, the density function of xy of x comma z minus x, if they're independent, simply just becomes the integral of negative infinity to infinity of f of x for the first part, and then for f of y, it would just be z minus x dx. Now, this formula should be very familiar. It is simply just the convolution. In this case, when we're solving with regards to x, it is just a convolution of y onto x. Y onto x. And similarly, for when we're solving the y, it's just a convolution of x onto y. So that is one way of solving this problem. Similarly, we can also use the unit step function to solve for this problem. And so we know that the mass function of z is just equal to the double integral of the density function of xy over the bounds of x and over the bounds of y, because the mass function is simply just the summation of all the areas under the curve for small f of y, so that all the densities. And so we can use a unit step function, because so essentially x plus y has to be less than z. So basically, in all cases where x plus y is greater than z, this function here does not exist. So similarly, just how a unit step function only exists for when x, or when for positive values, in this case unit step function x, all values positive and it's 0 elsewhere. Similarly, if we use a unit step function where it's a unit step function of z minus x plus y, if this value was greater than z, this unit step function would be negative, and then negative values of unit step function don't exist. So this function would go to, so this entire integral would go to 0 because it wouldn't exist. And so we can use the unit step function to essentially get to the same answer we got in the previous answer. So starting over, we have the double integral of small f of xy times x small f of xy of x and y times the unit step function of z minus the summation of x plus y. And so if we expand this, you get the same thing, except the unit step function is z minus x minus y. And depending on how you want to look at this step function, you can choose whether to solve whether in respect to x or with respect to y. And so if we just, let's say, put a parentheses here, and so this value has to be greater than y. Because if it was less than y, no, greater than y. Because if it was less than y, then this entire unit step function would be negative, and similarly, nothing would exist because there's nothing that exists as a unit step function of a negative value. And so that function will not exist. So this has to be, this function only exists the interval from negative infinity to z minus x. And so therefore these bounds is just negative infinity to z minus s of x, f of xy dy dx. And so this will be solving in terms of y. And just like you saw in the previous part, this is exactly the same thing if we solve for y. Exactly the same thing as what we have here. So we got to the same point, except here we use the unit step function. Both ways are valid, whether graphically or the step function. And then similarly, after here, you just calculate down to what we've done before, and you would get the same answer. So as you can see here, these two are the same. Similarly, if we solve for x, we simply just clump these differently. So instead of having z minus x minus y, we have z minus y minus x. So then therefore this value has to be greater than x. Because like I said before, if it was less than x, then this value would be negative, and the unit step function at a negative point is 0. So this entire integral would not exist. So we have to choose a value for where z minus y must be greater than x. So that's the bounds of the x here. Whereas last time we did the bounds for the y. We're now doing the bounds for the x. So it would just be the bounds of x from negative infinity to z minus y, and then, you know, the double integral from negative infinity to infinity for dy. And so, as you can see, like we did before, that is also equivalent to just this, where we solve for x. So these two are exactly the same. They both get you to the same part, but they're two different methodologies of getting there, and both are equivalent and will give you the same answer. So similarly, once you get here, you can simply just go back to what we've done before, and then you end up with these two different ways of producing the same density function for z. Thank you.